Welcome to our third and final mini lecture on cosmology. In this mini lecture, we're going to talk about the past of the universe and the future of the universe. I'm not going to go to the very distant past, the Big Bang. That will be our next unit, gets a whole unit to itself. But we'll talk about the more recent past of the universe and what may happen in the future. So this is from your first three sections of chapter 26. Our understanding of cosmology has a philosophical underpinning, and that's something called the cosmological principle. And the cosmological principle states that the universe is isotropic and homogeneous. Now, in case you don't use those two words in everyday life, isotropic and homogeneous basically mean that the laws of physics are the same everywhere and for all time, and that the part of the universe that we see is representative of the universe as a whole. So if you want to restate it into even simpler terms, Bill Keel, an astronomer at Alabama, says the universe is knowable and plays fair with scientists. Andrew Little, another astronomer, says that the universe looks the same no matter who you are or where you are, whoever and wherever you are. We have evidence that on large enough scales, the universe looks pretty much the same. Maybe not within our room, maybe not even within our solar system, but you go and you look out into space and you get large enough and there are galaxies everywhere, stars everywhere, all kind of spread out more or less equally over large distances. And the laws of physics, insofar as we can test them from far away, from say things like absorption lines and emission lines, those laws of physics seem to have been the same over all time. Now, because light takes time to travel to us, whatever we're looking at is not how the universe is now, but how it was some time ago. Light travels at a speed of about 1 foot per nanosecond. A nanosecond is 1/billionth of a second. So when I look across the room and see people across the room, I'm seeing them as they were a few billionths of a second ago. Now, most of the time, not much changes in a few billionths of a second. But if we start looking at bigger distances, like the sun is 8 light minutes away. That means it takes light 8 minutes to get to us from the sun. So if something were to happen on the sun, say a stellar eruption, that were sending charged particles our way, we wouldn't know it for 8 minutes until the light got here. And since those particles often go the speed of light, we wouldn't have 8 minutes of warning. We would just have a few seconds of warning. Pluto is 4 light hours away. So if we want to communicate with an alien on Pluto, we would have to wait 8 hours for a communication. 4 hours for it to go one way, 4 hours for it to come back the next way. In other words, let's say that we had a spaceship around Pluto and something bad were to happen on the spaceship, we would not know for 4 hours. Alpha Centauri, the nearest star to us, is 4.25 light years away. So if some alien baby were born right now and they sent out a blast of radio communications to every known civilization to announce that their new king had been born, it would be 4.25 years before we would know that it had happened. Betelgeuse. Betelgeuse is 650 light years away. If you go out tonight and look at Betelgeuse, the light you see left in about 1350 AD, or a good 50 years or so before the Italian Renaissance got underway. So you're looking at light that left during the Middle Ages. Betelgeuse may have exploded since that time. We don't know because that light hasn't gotten here yet. We see the star as it was 650 years ago when it was just a normal red supergiant star. Betelgeuse probably hasn't exploded yet, but there's a slight chance that maybe it has. The Hercules cluster is a cluster of stars 25,000 light years away. If you were to go out early in the morning before the sunrise, you could see the Hercules star cluster with binoculars or a small telescope, and the light that you would see from those stars left those stars before modern civilization, when humans were still living as nomadic peoples. If you're familiar with cave paintings in France, many of those were made 25,000 years ago. So that's how long it's taken the light to get to us, and the Hercules cluster is still within our own galaxy. The nearest big galaxy to us, the Andromeda galaxy, is 2 million light years away. So the light we see, if you were to go out and look at it tonight, would be light that left 2 million years ago, before modern humans had come about on the Earth. Now, if the cosmological principle is true, that the universe is more or less the same in every direction, and since light takes time to get to us, what this means is that if we are looking at distant galaxies, we are seeing what the typical galaxies in the universe were like when the universe was younger. It's like, so our telescopes become a time machine that allow us to see what galaxies were like. Now, we're not seeing the Milky Way and Andromeda as they were 10 billion years ago. We're seeing different galaxies, but we assume that the galaxies that we do see are representative of what the universe was like. So the Hubble telescope has spent a lot of time studying these very distant galaxies. And what it has found is that distant galaxies are smaller in both size and mass than galaxies today. We see that distant galaxies are merging much more often than galaxies are today. And we see that distant galaxies are forming stars much faster than galaxies are today. And so without much further thought, what this tells us is that the universe used to be different than it is now. In other words, the universe is changing over time. It's not static. It's not staying exactly the same. This picture shows some of these distant galaxies, and of course size is hard to go by because these are so far away, but you can see that a lot of them have faint companions, a lot of them have bright centers, which are often indicative of strong star formation. These don't look like normal everyday spiral galaxies. One final bit of scientific philosophy to throw into the mix here is something called Olbers' paradox. And Olbers was a German astronomer back in the late 1700s, early 1800s, and Olbers asked, why is the sky dark? I mean, it seems obvious to us because the sun's down, but that's not the full answer. If the paradox comes from a thought, if the universe is infinite in size and infinite in age, then everywhere we look we should see a star. Everywhere we look we should see a star, which means that the entire sky should be ablaze with starlight. If you work it out mathematically, you find that even though stars look dimmer when they're far away, there would be more of them in a given area of the sky, and so the entire sky should be as bright as the surface of the sun. And it's not, it's dark. Here's another way of thinking of it. Here's a picture of a dense forest, and if the forest is big enough, like this one, even though trees are rare, you can see there's lots of space in between the trees, but if you look off into the distance, if you look far enough, every direction you look, you see a tree. So if a forest is big enough, you'll never see the edge of the forest. You'll always see a tree no matter which way you look. And this is what Olbers was thinking about with the universe. If the universe is full of stars, which it seems to be, now remember at this time, around 1800, we did not know about galaxies, but this same argument works for galaxies as well. The universe is full of stars or full of galaxies, even if they're spread far apart. If you look far enough, no matter what direction you look, you will see a star or a galaxy, and the whole sky should be as bright as the sun. Here's a picture of the sky from the Hubble telescope, and it's here to illustrate the obvious. Yes, we do see some galaxies and stars when we look, but most directions we look, we see dark sky. There are not galaxies everywhere. The only way to resolve this is to say that the universe is not infinite in age and or not infinite in size. So if we combine our knowledge of the expanding universe, the finite speed of light, the cosmological principle, and Olbers' paradox, we come up with these implications. First of all, the universe is changing. It's not static. Second, when we look further away from the Earth, we're looking further into the past. And third, In the past, everything was closer together because the universe is expanding. And if you go back far enough, you find that 13.7 billion years ago, everything was in the same spot. Every star, every galaxy would have been in the same spot. And this implies that the universe had a definite beginning. Now, most of you will not find this an astounding statement, but for astronomers in the mid-1900s, this was an astounding statement because the prevailing idea had been that the universe had always been and would always be and was unchanging. And you see that these three things put together tell us that the universe is changing and it had a definite start. And if you use our modern measurements, that start was 13.7 billion years ago. We will talk about this definite beginning, what we call the Big Bang, in our next unit. So now let's talk about the fate of the universe. We know the universe is expanding now, getting larger, and from dark energy, the rate of expansion seems to be getting faster. So what happens next? Here are some cartoon models. Let's go through these one at a time on the following slides. One option for the future of the universe. The universe started off small, it's expanding now, and if there's enough matter in the universe, then gravity will be strong enough to slow the expansion of the universe, stop it, and cause the universe to recollapse in on itself. However, if we add up all the matter we can see, and we can include dark matter in this because dark matter has gravity, we only have about a quarter of the mass we would need to cause the universe to recollapse. So this option does not seem like what's going to happen. Our second option, if you have just enough matter in the universe, gravity can slow down the expansion and bring the expansion to a stop after a long period of time, but gravity would not be strong enough to bring it back in. This is what's called the critical case of the universe. So in this case, the universe will get larger and larger and larger, but over time that increase in size will get slower and slower, and hundreds of billions of years from now, trillions of years from now, it would look like the universe is just barely expanding, but there's not enough material to bring it back in. This option also seems to be ruled out because there doesn't even seem to be enough matter to slow down the expansion of the universe by this much, even if we include dark matter. So we throw this in here for completeness, but it doesn't seem to be what's going to happen. A third case, dark energy. We know that dark energy is causing the expansion of the universe to accelerate. So what if the expansion of the universe accelerates for all eternity? This would mean that the universe would get larger for all eternity, and over time it would get larger faster. It would grow exponentially in size. Now in a universe like this, the expansion would not rip apart galaxies. Gravity would continue to hold galaxies together, hold stars together, hold the Earth together. But it does mean that the universe would live for an infinite amount of time and get infinitely large over that time. And as of right now, with everything that we know today, this is what would happen to the universe, and we would be the solid line always getting bigger. In a universe like this, which we think is where we are, although we're not positive, galaxies will move further apart, and when the last stars run out of their fuel, they'll become white dwarfs. The white dwarfs will cool off over time, neutron stars will cool off over time, there won't be any new stars, and so the universe will become dark. A dark, cold, mostly empty space with the occasional galaxy here and there made out of dead white dwarfs, dead neutron stars, and black holes. So this is a picture of what we think the universe will look like in the distant future. Not a very happy picture. However, there's one other picture that's even worse. If you thought being in an eternally expanding, cold, dark, empty universe was not enough, there's a worse option, and that's option 4. If dark energy changes over time, and if the acceleration gets faster over time, there will come a point in the future, maybe as soon as 20 billion years from now, maybe trillions upon trillions of years from now, but the universe will be expanding so that the fabric of space-time is trying to expand faster than the speed of light. That can't happen. And so this would rip apart even the fabric of space-time. And rip apart everything within the universe. All the galaxies would get ripped apart, and then all the stars would be torn apart, and the planets would be torn apart, and you would be torn apart, and your atoms would be torn apart. This is something called the Big Rip. And so just as a cartoon of what would happen over time, the universe just expands so fast that at some definite point in the future, everything in the universe would be ripped to shreds. Our knowledge of physics would end at that point. We don't know what would happen afterwards, if there can even be an after. So this would be a universe with a definite start, a definite end, and it wouldn't be a pleasant end either. This seems unlikely, but we can't rule it out. Again, it depends on what dark energy is, and we don't know what dark energy is. Let me go back to summarize what we've learned in this mini lecture. We've learned that cosmology is based on a principle, quasi-philosophical principle, that the laws of physics are the same everywhere, and the universe looks more or less the same every direction you look. If you don't allow that to be true, then you can't do any physics and understanding of distant stars, but all the evidence we have points to that this is a true principle. Allowing for this principle, allowing for the expansion of the universe, this tells us that when we look deeper in space, we're looking further in time, and we see that the universe is changing over time. It's not always the same, and that at one point in the distant past, everything would have been in one place. And that's what we'll come back to in next week's unit. Looking into the future, it's always dangerous to project, but there are several options for the future of the universe. This one seems to be the most likely right now. If dark energy is Einstein's cosmological constant, then the universe will expand at an ever-increasing rate. Eventually, all the stars will die out, and the universe will become dark, cold, rapidly expanding chunk of more or less empty space. And on that happy note, we'll end this mini lecture and this unit.